water has some very important physical chemical properties which are fundamental to mediate these functions. So it's not electrically charged, but it possesses a dipole because the oxygen works as an electronegative atom, so it tends to attract electrons. And so the molecular orbital of water has a partial negative charge towards the oxygen and a partial positive charge between the two atoms of hydrogen. So it is a charged dipole, and by being a charged dipole, it can disrupt the ion bonds between ionic compounds such as silver chloride. And silver chloride in water exists as, sodium chloride. So silver chloride is a compound indeed, but is not, and it can be dissolved in water for sure, but it's not what I meant. Sodium chloride I meant, which can be, dissolved. And the process of dissolution consists in the dipole of water forming a shell of waters around sodium and chloride themselves. Then these dipoles can interact with each other, forming, the so-called hydrogen bonds, which is nothing else but the sharing of an atom of hydrogen between two atoms of oxygen. It is not a covalent bond, and you can experience the presence of hydrogen bonds on a day-to-day basis by looking at the surface tension properties of water in a glass, by seeing how the surface of water is resistive to being pierced. So actually water has pretty high surface tension, and the presence of these bonds actually make water a great reservoir for heat and a great heat sink, as a matter of fact. It has very high specific heat and latent heat evaporation in comparison to other substances, which makes water a fantastic coolant agent. Water is, for example, being used as a cooling agent for nuclear centrals. And this is not due just to the fact that we do have a lot of water accessible, which we do, but also because water is in itself a great coolant, which means that it can absorb and release large quantities of heat without great changes in temperature. So body fluids, of course, contain water, as we said, and inside of water we have a series of solutes, which are electrolytes, which are the ion-charged species of salts, such as sodium, potassium, calcium chloride, and of course proteins, which form colloids, and which are negatively charged in solution. And also we do have non-electrolytes, which are usually polar molecules, which are not electrically charged, but they do have partial charges around them, such as polyalcohol, such as glucose. And note, blood cells are not solids. They're definitely not electrolytes. They are cells. Okay, they're not part of the body fluid. If you take out the blood definitely is a liquid, but it's composed by two components: a cellular component, which are cells with a plasma membrane and intracellular space and so on and so forth, and the plasma, which is the fluid itself. So when you're talking about body fluids, you never refer to the fluids contained inside of cells, but I always refer to the internal environment. This is very, very important. So here's a table. I mean, of course, I can't pretend you memorize all these values, but it is important that you do understand what goes on here. It is important that you do understand that there are some patterns here, right? Especially when it comes to sodium, potassium, and calcium. So you do see that the plasma concentrations of sodium are high, while the intracellular concentration of sodiums are low. And you can see that pretty much for each one of these values, there's more or less a correspondence between plasma and the interstitial fluid, because there is a continuity between. While there is a difference between, what is the internal environment, which is, plasma, interstitial fluid, and transcellular fluid, and the intracellular fluid. In particular, we do have relative high concentrations of sodium extracellularly and low concentration of sodium intracellularly, low concentration of potassium intracellularly, and high concentration of potassium intracellularly. Two orders of magnitude in difference, actually 3 orders of magnitude of difference in the concentration of calcium between extra and the intracellular compartment. And this is very, very important. It is one of the reasons why calcium is used as an intracellular second messenger. Magnesium chloride, phosphate, look at glucose. The concentration of glucose extracellularly is pretty much constant, but there is no glucose inside of the cell. Once the glucose is inside of the cell, is instantaneously used. All these components adding up together in terms of milliosmolarity, milliosmol per liter, will give you an osmolarity which is the same between the plasma and the between the intracellular space and the interstitial space and the plasma. And this osmolarity is around 280 milliosmol per liter, and a constant osmotic pressure. This is fundamental to ensure there's always, a net amount of water that doesn't exchange between compartments. It is important that the net movement of water between compartments is equal to 0. So the number of osmoles per liter, and we will go through these in week 24, where I will give you a reminder of osmolarity calculations, doesn't correspond to the number of charges, but to the number of free ions. Now, always remember that our body is not charged. So the overall amount of charges inside of the cell is balanced and is counterbalanced by the number of charges outside of the cells. Always remember that the number of ions doesn't correspond to the number of charges. It depends how many charges each ion contains. So if we make a little exercise, and we count the number of ions inside of our cell here, we can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. I think I'm counting 9 positive. Yes, that's correct. And 1, 2, 3, 4, 5, 6 negative. Yes. And in the negative is also included protein. But the number of charges changes. Number of charges changes because each ion contains, potentially different amounts of charges, right? So potassium and chloride, cancel each other out because potassium is positively charged and chloride is negatively charged. So if we look at the number of positive charges inside of the cell, we'll see that the number of positive charges is 1 potassium, 2 potassium, 3 potassium, 1, 2, 3, 4, 5, 6, 7 with sodium, 9 with magnesium, and 11 with the other magnesium. So that should be, yep. And the negative charges will be -1 with the chloride, bicarbonate, 1, 2, 3, 4, 5, 6, 7. -11 for the negative charges as well, because we've got 4 negative charges on the protein, -2 negative charges on the hydrogen phosphate, 1 negative on the dihydrogen phosphate, another negative on the bicarbonate, another double negative on the dihydrogen phosphate, and 1 single negative on chloride, and that's the total of 11. As you can see, electrically, the inside of the cell is neutral. Within each fluid compartment, the ionic charge is equal, even though the number of ions changes. So this is very important for you to remember. Each one of these ions may have many different functions. So sodium is definitely the most important contributor for the osmotic gradient and for the generation of osmotic pressure. It's also very important for the generation of action potentials through the generation of inward currents once the voltage-gated sodium channel is triggered. Potassium is the main, well, it's also another contributor to the osmotic pressure of the cytoplasm, but it's also very, very important, especially, you know, the intracellular concentration of potassium. Very, very important. Well, the difference between intracellular and extracellular is very important for driving the resting membrane potential of a cell, and this is due to the fact that cells have a very high permeability to potassium in resting conditions. It's also very important for you know, mediating the repolarizing phase of an action potential. Calcium does all sorts of things. I always used to joke when I was a student that if you didn't know an answer to, you know, any random question you could have been asked ever in 5 years of biotechnologies, you could have put calcium and you would have got a point somewhere because it's basically involved in everything. Here I've listed regulates muscle contraction, regulates the activity of many enzymes, regulates exocytosis, which is all true, but it's definitely reductive. It's a second messenger. It's important in the generation of action potentials. It's important in synaptic plasticity. It's important in cell-to-cell communication. It's important in apoptosis. It's important in cell proliferation. I could go on forever. Magnesium, it's also a very important ion. Yeah, other than being a cofactor, to me, magnesium is an important cofactor, especially because of its function on PMDA receptor as a neuroscientist, because the magnesium block is what blocks NMDA receptors. And if you excite a cell enough in presence of glutamate, you can activate an NMDA receptor, which then induces the generation of memory in the hippocampus. So that. Hydrogen phosphate, dihydrogen phosphate, bicarbonate basically are intracellular systems and extracellular systems for buffering the concentration of protons. And finally, chloride, which follows sodium wherever it is. And it mostly works as a counter ion. Chloride is very, very important in also driving the resting membrane potential of a cell and in regulating osmotic pressure. Remember that alterations in chloride channel has very severe consequences for the body. Think about cystic fibrosis, think about cholera.